Thank you for watching this video. I hope you're all doing well. In this talk, I will tell you about SleepBandits, our system for guided and flexible self-experiments for sleep. Right now, people track all kinds of data about themselves. For example, their blood glucose, their cycles, their productivity, their mood, their sleep, and so much of that is done with the help of self-tracking technologies. Thanks to this quantified approach and the ubiquity of these devices, in the future, every health and lifestyle recommendation that we follow could be personalized. But right now, we still follow this generalized advice that might not be applicable to us in the specific outcomes, and it could lead to negative consequences. For example, in biomedical research, data derived from male subjects for diagnosis and treatment has long been considered a one-size-fits-all. Overall, the generalizable advice that we've heard might not necessarily apply to us in the exact way that it's prescribed. Now, this talk is not focused on medical breakthroughs, but rather on much smaller lifestyle changes that we can make in our daily lives. One approach to figure out what works for each person individually is for people to conduct experiments on themselves, called self-experiments. They can help identify causal relationships between variables in our lives and help us draw personally meaningful conclusions from the data. The goal is to find out what works for each specific person rather than finding generalizable knowledge that can be disseminated to the public. So even though these technologies help us track all this data, they do not provide the tools to self-experiment. So what happens is that when someone wants to conduct a self-experiment, they have to design the whole setup and analyze the data on their own. But most users are not trained to conduct scientifically valid experiments. So they end up conducting internally flawed ones that result in misleading conclusions. In our previous studies, we saw examples of just that. One novice had designed a study with the hypothesis that reduced phone usage during work hours would improve their work productivity. The first 2 weeks he would use his phone as normal, but the second 2 weeks he would limit it during work hours. This looks reasonable, right? Well, the issue is that that person was a student, so their productivity in the way that they had defined it depends a lot on whether it was a weekday or a weekend. And he didn't realize that spring break would include most of the days during the restricted phone usage, so there would be no work or work hours to be productive at. This introduced confounding variables and flawed his experiment. However, if he had just flipped a coin to randomize which condition to follow each day, then his experiment would not be as flawed. The current state-of-the-art systems are not optimized to balance the scientific rigor and real-life adherence, meaning that they are often too rigid and demand a set schedule to track. They ask people to track a behavior over the course of weeks in order to estimate its effect. For example, Quantify Me was a great step towards such systems. It asked people to follow a rigid schedule for 16 days, and if they didn't follow it in enough days, then the experiment would restart. So only one of their 13 participants managed to finish an experiment. That's not a practical design when you have real life that gets in the way and disrupts the routine. On the other hand, a system like like tummy trials, for example, let patients with IBS set up an experiment with the help of their doctor. However, not everyone has access to doctors that can help them conduct and analyze a self-experiment. Our lab also had an initial system for self-experiments, which asked people to follow this timeline for their experiment. During the yellow days, they would live their lives as usual, but during the green days, they would follow the behavior change that we asked them to. And in this particular setup, participants were told exactly what the behavior change would be. For example, go to bed at 11:30. So they were not given any freedom on what they were assigned to do. And then at the end of the 3 weeks, we would calculate the result and let them know whether the change improved their sleep or not. From that study, we learned that people would like to be able to end their experiment earlier and not to have to spend 3 weeks on one given experiment. They also liked being told what to do on every single day, so the daily guidance, but they wanted agency in their own experiment choice. They didn't like being told what to experiment with. And finally, they wanted easy to understand results and an analysis that could handle the missing data from when they forgot to use the app. These findings led us to the question of how can we build a self-experimentation system aimed at balancing scientific rigor and real life. Based on all the prior work, we've designed this set of principles for practical self-experiments that we can address when we develop such systems. The first one is guided agency, meaning that we should give users not only the flexibility to choose their own hypothesis and experiment length, but we should also nudge them towards best practices. The second one is scientific rigor, which means that we should help users incorporate randomization in the experiment. Next is tolerance, meaning that we should be able to accommodate real-life circumstances such as missing data because real life can get in the way. And lastly, comprehensibility, meaning that we should present the results in a way that's easy to understand, so not the p-values that are usually typical for our kinds of studies. We use these principles in order to design SleepBandits, our system for guided and flexible self-experiments. To see if our experiments work, we decided to focus on a single domain, so we chose sleep. Sleep is the most commonly tracked variable for self-experiments because of the ease of automated tracking. It lets people measure their time to fall asleep and the wakenings per hour with the help of devices like Fitbits and all the apps that you can download even for free from the App Store. However, these apps and devices mainly provide just descriptive statistics and no actual recommendations. The SleepBandits app uses the accelerometer and microphone in the phone, just like most of those apps, to track your movement and noise levels throughout the night. It asks the user to keep the phone on the bed overnight in order to be able to do so. One of the main features of the app is the list of experiments. They were all pre-approved by our clinician collaborators, and they're all things that you can do today to see how they immediately affect your sleep tonight. For example, does listening to an audiobook help you fall asleep faster or not? And then on the home page, you see the instruction for the day on the top, and then you see your current experiment in the middle, and you're able to change it at any point. And then at the bottom is the result. Then if you were to track your sleep, you just have to tap the track sleep button on the bottom, which takes you to a pop-up which reminds you what your condition for today is. For example, today wear earplugs, as well as asking you to rate how sleepy you are. And then it starts tracking when you click done. Then when you wake up in the morning, a pop-up also appears, again asking you how tired you feel, but also asking whether you adhered to what the app asked you to do. All of our design choices, including the reasons behind setting up the user flow like this, are described in the paper. And then finally, after a few days of collecting the data, the app gives you a result. It analyzes everything for you, and you're able to decide whether you want to stop as soon as you see the experiment, the result, or if you want to keep going after. If you keep using the app, the results will just keep updating every day. In order to be able to do that, we needed an analysis method that lets the user stay in the more helpful condition more often, and also adapts to incoming data and lets the user stop the experiment early. Usually that can be done with Bayesian analysis, and also provides an easier to understand result. So for example, p-values, because that's, for example, probabilities rather than p-values, because that's what previous research has shown is easier to understand for novices. That's why we chose to use Thompson Sampling, which is a heuristic for the multi-arm bandit algorithm. You can read more about it in our paper, but just as an overview, the multi-arm bandit problem is a problem in which a gambler sits at a row of slot machines and has to decide which machines to play and how many times to play each machine. When played, each machine provides a random reward from a probability distribution for that machine. The objective of the gambler is to maximize their rewards. So in terms of our system, if we have one machine that's, for example, listen to an audiobook and the other one is don't listen to an audiobook, the goal for us is to fall asleep as fast as possible. So in the beginning, there's a 50-50 chance that either condition will be better for us. So we're just exploring both conditions an equal amount of times. This is the result that the app will show after those 4 days of data. There's a 51% likelihood that you fall asleep 4 minutes faster if you listen to an audiobook. This likelihood percentage is also the probability with which we ask the user to follow that condition today. So the sentence on the top summarizes that information, and the numbers on the bottom provide more details. But as we're collecting more data, we learned that we fall asleep faster as we listen to an audiobook. So we start exploiting it by doing that more often. So now there's an 84% chance that the person will be asked to listen to an audiobook today. To evaluate the SleepBandit system, we released the app on the Google Play Store. We wanted to see if the experiment length affected the completion rate, so we randomly assigned users to two groups, 4 days or 10 days. That means that for the people in the 4-day group would see the result immediately after the 4 days are over, versus those in the other group would have to wait 10 days before they saw a result. We conducted quantitative analysis on 365 users and thematic analysis on the data from another 10 participants. The details findings are in the paper, but here we will highlight just a couple of interesting points. Overall, we found that people who conducted shorter experiments, so the 4-night group, were almost 3 times more likely to reach a result. This could be due to the natural usage of the app. This is the curve. It is interesting to note, however, that while the curves for the two groups are relatively similar, there is a dip in the 4-night group around the 5th day. This implies that people who saw a result on the 5th day, so the shorter group, were more likely to stop the experiment at that point. Another interesting finding was that users who received a likelihood percentage between 65 and 85%, for example, the person on the left, were more likely to stop the experiment, whereas those with really high or low likelihood scores, like those on the right, like 95% or 51%, chose to continue the experiment. Overall, our 4 design principles helped us create a system for self-experimentation that users say they would recommend to a novice. While there are multiple ways that we can improve them in the future, these principles can be used as a basis for future systems. We also learned that short experiment could lead to higher completion rates, and that Thompson sampling can be used to analyze the result of the self-experiment, both of which will hopefully serve as implications for design in the future. I would like to just point out that it took a couple of years to get our app to a stable enough version to be added to the App Store. Over the years, we interviewed almost 100 people about the UI of the app, and the feedback helped us iterate it numerous times. In the future, we can further improve the system by finding ways to alleviate the burden of tracking the user and encourage them to track more often by perhaps visualizing their progress toward the countdown of the results. In addition to that, in its current state, SleepBandits only focuses on experiments that have minimal carryover effect, so this approach might not work for the cases where it takes a few days to see a result. And for example, if there are long-term benefits of exercising or sleep quality, but our system would not be able to capture those. So in the future, we can expand our approach to experiments with carryover effect and to domains beyond sleep. If you would like to download the app for yourself, you can search for Sleep Culture on both the iOS and Google Play stores, and you can go to sleep.cs.brown.edu for our open source code. Our paper contains a lot more detail on our design choices, methods, and findings. Thank you so much for your attention, and I hope you stay well.